Okay, so let's carry on with looking for maxima and minima for functions. This is section 4.1. Okay, so um, we need a definition here. So a number c in the domain of a function is called a critical number or a critical value if one of the following things happens. If the derivative at that point is 0, then c is a critical number. Or if f prime of c does not exist. So if either of these are true, then we say that c is a critical number. Okay, and basically those are the places where a local max or local min might occur. It doesn't necessarily occur there, but they're the only places where a local max or min could occur. So that's called Fermat's theorem. Um, and Fermat is a French name, so it looks like Fermat, but you don't say the T, so it's Fermat. If f has a local max or min at c, then c is a critical number. It doesn't go the other way around. We can't say if it's a critical number, then it's a local max or min. That doesn't follow, but this way is true. And what that means is that we should look for local max, they're called extrema. Extrema means max or min. We should look for local extrema at the critical numbers. And just a note here that if we're dealing with a closed interval, the absolute max or min might be at the endpoints. And in that case, the absolute max would be it would not be a local max or minimum. That's not considered a local max or min. I'll just say that again. If a point at the end is not considered a local max or min, even if it is higher, because it doesn't have an interval around it. Okay, so let's say we're dealing with this function, and we're trying to find the critical numbers. So that depends entirely on the derivative. So first find the derivative. And let's see here. So how do we find the derivative? Well, let's first rewrite the function as using a fractional exponent. That's going to make it easier. Cube root is 1/3. So now we can find the derivative. So bring down the exponent and subtract 1 from the exponent gives us minus 2/3. And now times the derivative of the inside, which is negative 2x. Okay, so critical numbers are, one, where the derivative is 0. That's saying that. Now let me actually write this in one more way, which is I'll put the negative exponent down in the denominator. And that 3 is down there too. So when is this equal to 0? It's the only way that that's equal to 0 is if the numerator at the top is 0. That implies that negative 2x is 0, which tells us that x is 0. So that's one critical value, critical number. Or we look for places where the derivative does not exist. And when does that happen? In this case, it's when the expression is undefined. It does not exist when this denominator is 0, because then we'll get something over 0. So how do I solve that? Well, I can cancel the 3, and that will for this to be 0, the expression inside here must be 0. And then I can see that would be x is plus or minus 2. So the critical numbers are critical numbers of f are c equals 0, minus 2, or plus 2. Maybe I should say and. All three of them are critical numbers. All right, and now what do we do with that? Well, those are the places where there could be a local max or local min. So we're going to use that in the next step here. Find the absolute max and absolute min of that same function. So we are going to check the critical numbers, which we just found. C is 0 or plus or minus 2. And we're going to check the endpoints, which are x equals, oh, well, what is the domain? We don't know the domain. But we have to do that first. So the endpoints, which we don't know yet. So are there endpoints? So let's think about the domain here. Now, what do we need for the domain? We need to have, do we have any restrictions here? Let's think. So it's a cube root, right? For a cube root, let's call it cube root of u. U can be anything, right? It doesn't matter if it's negative. So that means that this 4 minus x squared can be anything. So that actually means that the domain is all real numbers. The domain is the interval from minus infinity to plus infinity. So we actually don't have any endpoints here. The domain is everything. No endpoints. But what we have to do, in a sense, we still have to check what happens at plus infinity and minus infinity. So I'll show you that in a second. We still have to see what happens as x goes to infinity or negative infinity. Okay, so what are the critical, what do the critical values give us? F of 0 is cube root of 4 minus 0 squared, which is the cube root of 4. And it helps if we have an exact value for that, just for comparison, so 1.587. What about the other critical numbers? So that's 4 minus, so that's the cube root of 0, which is 0. And for minus 2, I think it's going to be the same, right? Because it's x squared. So that's also cube root of 0. Okay, so now at this point, it looks like this maybe is the absolute max, and then 0 is an absolute min, right? Now, we can't be absolutely sure yet, because what if the graph goes up to infinity as x goes to infinity? So the last thing to check is the what happens as x goes to plus infinity. This is kind of like an endpoint, right? It's an endpoint at infinity. So the limit as x goes to infinity of 4 minus x squared cube root. Now let's think about this. If x is very large, then we're going to get a negative infinity in the cube root, right? So we can think of it like this. I'm imagining what happens here. So this will become negative infinity, cube root. That's going to be negative infinity. What about the other way? If x goes to negative infinity, negative infinity. Well, it actually gives me the same thing because the squared there, um, the square means it doesn't matter that it's going to negative infinity. This will still go, when I square it, it becomes plus infinity, but then there's that other minus sign. So that's also negative infinity. So what we know is that the graph looks something like this. Well, let's actually use Desmos, but what we know is that now the absolute min, there is no absolute min. Absolute min does not exist because the function, because f of x goes to negative infinity as x goes to either plus or minus infinity. So it just goes down, down, down. There is no bottom. There's no stopping point. The absolute max is at x equals 0. Let me write it this, is absolute max is f of 0, which is cube root of 4, which occurs at x equals 0. Great. So let's double check that with Desmos. Let's make sure we've got everything right. So what is it? F equals 4 minus x squared to the power of 1/3. So it's a cube root. Okay, so looks like we got it, but let's actually make this a little bit nicer looking. Okay, and this can be, I don't know, negative 10 to 3. Okay, so that's what this weird function looks like. It has its highest point right in the middle, and then it goes down to the right and the left. Okay, let's paste that in there. So one of the things that we're going to be using derivatives for pretty soon is sketching these functions. So we'll be able to do more of this ourselves. Okay, I can leave it right there. So we found the absolute max here. And there's no absolute min because this goes down forever. All right, so we'll do a couple more kind of conceptual examples here. Sometimes the absolute max doesn't exist. Sometimes the absolute min doesn't exist, like we just saw. So let's think of some examples here. So sketch the graph of a function defined on -1 to 2, where it does have an absolute max, but no absolute min. So let's think about that. So there's -1, -2, 1, 2. And so all I'm going to do is just sketch it. It has a max, but no absolute min. And it's defined on that interval. Okay, so here's one thing I can do. I can make it have an absolute max right there. But let's say it goes down to negative infinity like that. So it has a asymptote. But it has to be defined there, so I'll just give it a solid dot there and finish it up like that. So there's no, so this one has an absolute max right here, but no absolute minimum. So that one's kind of like our previous example, except I didn't even need x to go to infinity. I can make it happen at a finite point here, like 1. So let me just make this slightly clearer. So if I put an arrow there, it shows that it's going down forever. Okay, let's do another one. sketch the graph of a function that is discontinuous but has both an absolute max and an absolute min. So you might say, well, what does continuity have to do with it? Well, there's actually a close connection that we'll see in a minute in the next video. Okay, so now we're going to go from, so it has an absolute max and an absolute min, but it's discontinuous. Well, that's not so hard to arrange. I can make it have a max there, and then it has, let's say, a jump, and then let's say it has an absolute minimum right there. So there's the absolute max, which is also a local max. And then down here on the endpoint, I have an absolute min, but it's not a local min. Okay, why is it not a local min? Because there's no interval around that point that where the function is defined. Okay, so last one. Now here we have to think, the graph shown is the graph of the derivative. So we're being shown the derivative of a function. And the domain is from 0 to c. Find all values x at which f has local extrema. So either extrema means min or max. So remember the local min or max, they occur at critical numbers. Which is where f prime of x is 0 or f prime of x does not exist. So in this case, it looks like the derivative exists everywhere, but it's 0 at these 2 points. So that means x equals a and x equals b are critical numbers, are the two critical numbers. So those, if there are any local max, they occur at those places, local extrema. So let's think here. What do we know about f of a? F of a is local what? So we have to use some reasoning here. So to the left, if x is to the left of a, that means that f is increasing because its derivative is positive, right? And if we're to the right of a, f is decreasing. So we know that as you get to a, the function is increasing, and then after a, the function is decreasing. So that means it must be a local max. It's a local max because, I'll just say it again, f of x is increasing to the left and decreasing to the right. Okay, similarly, f of b is a local, no, actually we have to be careful here. F of b is neither, f of b is decreasing on both sides. This is the derivative, remember? So f prime of x is negative on both sides of b. So f of b is neither a local max or a local min. Because f is decreasing on either side. On each side of x equals b. So last question, where are the absolute maxima and minima? Well, I'm just going to be brief here because I actually need to end this in a moment here, but f of a is the absolute max because, why is that? Basically, the function is increasing here. The function is increasing up to the point where you get to a, but then it's decreasing everywhere else. It's decreasing and then it's decreasing more. So because it's increasing to the left and decreasing to the right, it's the same reason it was a local max. What is the absolute min? The absolute min is it's actually ambiguous here. It might be the it might be either f of 0 or f of c is the absolute min, but it's ambiguous. Okay, and I have to leave it there. We can discuss that a little further in person if we need to. Okay, see you guys in the next video.